Hello, everyone. We're going to be looking at Chapter 2, Minerals, which are patterns in nature. Okay, so if you've ever get to go on a geology field trip, it's lots of fun to collect things. People carry rock hammers. It can be hot, it can be cold, it can be muddy, it can be rocky, usually sandy, all sorts of fun things, buggies, all sorts of good stuff. Anyway, rock clubs do have expeditions to look at minerals, and if you're interested in searching for fossils or something like that, then I can recommend some rock clubs around this area. There are 5 at least rock clubs in this area. Some are more active than others. So there's a fossil trip coming up pretty soon. Let me know if you're interested. Okay, so let's go look at minerals. All right, so this is showing some calcite with a laser shooting through it. We'll learn more about calcite. It's one of my favorites. And so we're going to break this lecture up into 2 pieces so that they aren't too big. All right, now your learning objective for the first part. Our first objective is to list the main characteristics that an earth mineral must possess to be considered a mineral and to describe each. Because it is always confusing. What do we mean by mineral? How is that different from a rock? Okay, so minerals are called the building blocks of rocks. So, in other words, rocks are made up of minerals. Since they build the rocks, then of course they build the earth. There are more than 4,000 minerals, and new minerals are often discovered, and new rocks discovered every day or very often. So it's something that is happening all the time that there are new minerals, particular combinations of elements that are put together in different ways. Now, people have been looking at minerals for many thousands of years, and so it's something that's very important. It's very important right now in the world, and especially as we're looking into electric cars and climate change, we're looking into battery storage. We need the minerals for batteries. So what we have are some countries have more minerals than others. And of course, it would be nice if all minerals were extracted in an environmentally conscious way, and that didn't exploit people or the environment. But that's often not true. Okay, so that's something we want to keep in mind also as we go through and as you answer questions in your homework. All right, so our society depends on mineral resources. Did you drive a car today? Then you depend on iron, right, in your car. And there might have been zinc and nickel and aluminum, of course. All those metals are extremely popular in our lives. Um, did your house have copper pipes for water? Is there copper wiring in your house that carries the electricity? Quite likely there is. Now, lead, we've tried to get out of our lives because lead can be dangerous, but it's an extremely useful material and it's still around. So, you've probably heard about the lead pipes that are causing trouble as we have aging infrastructure and old lead pipes and old lead joints of pipes. So anyway, so all of this stuff can really affect your lives. Non-metals, we have gypsum, which is very important, and limestone, clay. All of these things are in your lives. And so aggregate rocks that might be used to put in concrete or line roads. Um, all of this stuff are things that are in your lives every day. Here's some beautiful examples. Now, azurite is a gorgeous stone, but often it is just mined for the copper content. So it's a beautiful material. Copper often has blue or green colors associated with it, and we'll be looking more at that later. And down below that is some beautiful satin spar gypsum. It looks too pretty to grind up, but that's what often happens. The satin spar variety is a pretty type of gypsum. You're going to be seeing in your samples for your lab some gypsum that is not as pretty. And we'll look at satin spar gypsum several times because it has some interesting properties. Okay, so when we look at minerals, what we're looking at are things that are in our lives every day. They're economically important. They drive world economies. So right now, some countries are still digging coal, almost every country. Um, they're precious minerals and rare minerals that are needed for us to make into things like our cell phones, our computers, our homes, and because of that, we have to enter into negotiations with other countries. So it's something that really drives our economy. They're historically important because the search for minerals, the lust for minerals like gold and silver, that has, sponsored people into exploring lands and unfortunately usually taking over lands from people who already live there and exploiting um, manufacturing and mining and people. And so, anyway, so iron, copper, gold, diamonds, gems, all of these things are minerals, and they're all things that have driven society to interact with other societies, not always for the better. Okay, here's some more of that beautiful gypsum. There is a cave in Mexico that has 40-foot long crystals, and they did not destroy those. But certainly gypsum is very important, and we'll talk more about that later. Anyway, so what is a mineral? So gypsum is a mineral. And as you can see, it is naturally occurring. These are naturally growing in caves deep underground. Now, so it has to be naturally occurring. Another thing is it has to be a solid. So there's a reason for that, and that depends on the third definition here. It has to have a definite chemical composition. So if you have a fluid, which might be like, think of seawater. There's salt in the seawater, but some parts of the sea are saltier. There are fish swimming around in the seawater. There are particles in there. So you can't have a definite chemical composition in a liquid usually because you've got too many materials wandering around. So that's one of the reasons that it has to be a solid. The other reason is that it has to have an ordered atomic arrangement. Again, something that doesn't really occur in a liquid where the atoms have movement compared to each other. So anyway, so we're looking at solids, we're looking at definite chemical compositions, and an ordered atomic arrangement. Okay, so what else? Well, another thing is inorganic. Okay, it's not made by a plant or an animal. Okay, it's inorganic in that way. It can have carbon in it, but it's not made by life. Okay, so later you're gonna one of your homework problems you're gonna be looking at a list of materials and trying to determine if those are minerals or not. So make sure you come back to this definition. Okay, so the second part that we're going to look at here, your second learning objective for this first part of the homework of the chapter, is we're going to be looking at the three primary particles contained in atoms. So for a lot of you, this is pretty, you shouldn't, old stuff. You should know this stuff. Okay, so let's just go and quickly review three primary particles. And you're probably thinking, okay, protons, that's one, right? What's another one? Electrons, right? And maybe you can remember the third one. Starts with an N. Okay, well, let's go look at the periodic table a little bit and elements. Okay, so elements are the basic building blocks of minerals. You have a certain chemical composition for the mineral. So we need the elements in there. Now, the elements, there are over 100 that are known, and there are 92 naturally occurring. And then we've got some that people have put together by smashing together smaller atoms to make a bigger atom. And that's called nucleosynthesis, creating new nucleuses. Anyway, but the ones that are man-made, usually they decay very rapidly. They're not very useful because they're not very stable. Okay, so really we're usually looking at the 92 natural materials that are going to be making up our minerals. Okay, now atoms, those are the smallest particles of matter that retain all the characteristics of the element. And of course, we know what an atom looks like. So let's go look at that. Okay, so what do atoms have? Well, they have a central region called the nucleus, right? And in the nucleus, it has positive particles, oh, protons, of course, and negative particles. Oops, sorry, sorry. Negative particles are electrons, but in the nucleus, it's got neutrons, right? Neutrons are neutral. They have no charge. Okay, so you've got your nucleus of the atom, and then around the nucleus, you've got your electrons. And the electrons have negative charges. Now, this is a really bad drawing here, but it might be recognizable as a helium. Helium is number 2 on the periodic table, so it has 2 protons, 2 neutrons, and 2 electrons. Okay, now the electrons, as you keep adding more and more protons, you also get more electrons. And electrons exist in shells, energy levels. And so the further out you go from the nucleus, the higher the energy is. And so the electrons that are out in the outer shells would have more energy than the electrons on the inner shells. Okay, so we'll be talking more about that because the shells are very important to understand how atoms connect to each other. And by the way, why is this a really bad drawing of an atom? Well, almost all drawings of atoms are bad drawings of atoms because the size is always wrong. If we tried to have a comparison for the size of the nucleus compared to the size of the atom, then we really would have to look at something like a football stadium. Or imagine Soldier Field. And the nucleus would be like maybe a golf ball in the middle of Soldier Field. And the electrons would be like flies buzzing around on the outside of that throughout Soldier Field. So this shows that the nucleus is very, very tiny. So if you try to draw it, well, we can't really draw anything that's comparable and be able to see it. and then we would have to draw a really big shell. So we don't usually draw them that way because it just doesn't fit on our paper. Okay, so let's go look at a really bad drawing. Okay, so here's another really bad drawing because almost all of them are really bad drawings, as I was saying. Now, in this case, you can see that the protons and neutrons, they're packed together very tightly in the nucleus of the atom, and the electrons are zipping around on the outside. Now, another thing is to notice that this shell, okay, these are electron orbitals, and there are usually 2 electrons in each orbital. Okay, and it gets pretty complicated, and we're not going to get into it too much. But the idea is that usually electrons come in pairs. And a neutral atom would have an equal number of protons and electrons. So since I can count 8 electrons, then there should be 8 protons in the nucleus. Now the number of neutrons could be different. Okay, now here's another illustration of an atom. This one is trying to show you, give you some information about the shells. Okay, so the numbers that are in here, there's a 2, there's an 8, there's another 8, 18, 18, 32, 32. Those are showing how many electrons can fit into each shell. That's the maximum number. So the first shell can only have 2 electrons in it. But, and remember what a shell is. It's an energy level. That's a possible location for electrons. But some electrons might be in the second shell. The second shell can hold 8. And then the third shell can hold 8 also. But then it's 18, 18, 32, 32, which are crazy numbers. Okay, so let me show you, though, how that relates to the periodic table. And this, by the way, is what's called a conceptual model. Again, we're trying to distinguish some idea here that's helpful. We're never going to be able to draw what an atom really looks like. But we can sort of see how the electrons behave. So this model is helping us to understand where the electrons end up. Now, this is an actual photograph of the electron orbitals around a nucleus of an atom. But another thing is that electrons really aren't quite just one solid thing. We often see electrons as a wave. And so even though this atom, the electrons are moving so fast, you could say that they are all over the place. Even if it was just one electron, we would still be able to see these shell-like things because the electron would be jumping from one to the other. And we're trying to take a picture. And anyway, it's very, very complicated to take a picture. But here we have a nucleus. We've got an inner shell. And we've got an outer shell for the electrons. Okay, so let's look at the crystalline structure. As we said, the atoms in a mineral are specifically ordered. And so if we have disordered atoms, that's called a glass. So this picture here, this shows a glass. The atoms aren't in any particular order. So when we look at a crystal, like think of a beautiful quartz crystal, the atoms are in a definite structure, and that depends on how they bond to each other. But they have a beautiful pattern. So remember, this chapter is about the patterns in nature. Okay, so when we're looking at crystals, um, we often don't have flat external faces. This is what we usually see. We see this and we see this beautiful thing, but understand that those are the exceptions. Um, Crystals form their most beautiful shapes in open cavities. But the thing is, they fill up those cavities and then they run out of room, and then the crystals won't look so pretty anymore as they have to keep squishing into the space. So you have to catch them at just the right time to see a beautiful crystal like this. Okay, so one of the things we're going to be looking at later is about cleavage of atoms, of minerals. And so the atoms form a 3D lattice. And later when we talk about cleavage, we'll talk about the way that the atom will break along these lines where the minerals have these lattices. So, okay, so we're looking at patterns that repeat in 3 dimensions, and that controls a lot of mineral properties, like the crystal shape and symmetry. So what's symmetry? Well, that's where you have a mirror image, right? So, um, so the idea is that a snowflake has a beautiful symmetry, right? It has a mirror image. Okay, and here's a lovely material that involves sulfur and lead. Let me tell you, this one smells bad, but it looks really pretty. So we'll be looking at galena later. Okay, so let's look at bonds. Okay, so we're saying that the atoms are bonding together, and there are 3 main types of bonds that we're going to look at: ionic bonds, covalent bonds, and metallic bonds. Okay, so those lattices we were just looking at are held in place by atomic bonds. And so there are 5 recognized types: the ionic bonds, the covalent bonds, the metallic bonds, and then there's some that are called van der Waals forces, and there's another type called hydrogen bonds. So hydrogen bonds are what hold together water molecules in water. So in ice, right, we were just looking at a snowflake. Is a much more rigid structure, right? That's the solid. But when you've got water molecules, they're just loosely held. The hydrogen in the water molecule is slightly positive because it gave its electrons, shared its electrons with the oxygen. And so it is slightly attracted to the oxygen on another water molecule to the negative end. And that positive end of that one is attracted to the negative of the next one. So what happens is that you end up with the water molecules able to slip around each other. They fill up a volume, and so they're loosely held by those hydrogen bonds. Later, when we're talking about graphite, we'll talk about van der Waals forces a bit too. Okay, but what about ionic bonds? Well, famously, probably you know, sodium and chlorine form ionic bonds. And of course, the key word in here is ion. Okay, because an ion is a charged particle. And so ionic bonds are going to occur between charged particles. So let's go look at that more. Okay, so ionic bonding is the most common. And the compound that's formed, you have 2 or more elements. So remember, a compound is made up of two or more elements. Not just atoms, but different elements, two elements. So water, for instance, would be a compound. Um, so atoms gain or lose their electrons to form ions. And there's what's called the octet rule, which is where the atom wants to try to have 8 electrons in the outermost shell. We've got a nickname here of cation for the element that loses the electrons, so they become positive. So we were looking at sodium and chlorine. Sodium gives up its electron and becomes positive. The anion gains electrons to create a negative charge. So chlorine, famously, will accept the electron or steal the electron from the sodium and becomes the anion. Okay, but now that we have these oppositely charged ions, then they're going to attract each other. Positive and negatives are attracted to each other. And so you end up with a neutral chemical compound, so a neutral charge. Okay, positives and negatives cancel each other. Okay, now this is a simple version of the periodic table showing some of the names of certain groups. Mostly we're going to be looking at a lot of representative elements in the examples that we do. So the far left and the far right. And those are the ones that tend to make ionic bonds. And so sodium is going to be found over here. And chlorine is going to be found over here. Okay, far left and far right. Sorry, sodium should be here. So let's continue with this. And the elements in the middle are usually metallic. So that's where we're going to find our gold and our silver. And they, of course, will usually have metallic bonds. Okay, something else to note, the elements in this column are called the halogens. And of course, the elements in the very last column are called the noble gases. They don't make compounds, so we're not going to be seeing too much of those, but in minerals. Okay, and for covalent bonds, we're going to be looking a lot at atoms around in here, plus hydrogen. Okay, so let's look at those ionic bond, or looking at how we look at atoms in what's called the electron dot structure. So for one thing, we want to look at the valence electrons. Those are the electrons in the outermost shell of the atom. And so those are the ones that can participate in chemical bonding. So when you've got an atom, so here's our nucleus, we've got some electron shells. The one in the outermost shells, those are the ones that can be ripped off, or those are the shells that are unfilled. So usually you want to have at least 8 in the shell. So when we're looking at something like chlorine in the periodic table, chlorine is right here in the periodic table. It's in the 17th column, and that means that it has 7 electrons, 7 electrons in its outer shell. Okay, so these numbers here can help you. So the numbers 1, 2, and then 3, 4, 5, 6, and 7, and 8. Those are the number of electrons in the outer shell. And the idea is that the atoms want to fill in their outer shell. Okay, so we've got our chlorine over here, and it's in the 7th column of the what are called the representative elements. And so it has 7 electrons in the outer shell. Okay, so we draw just those 7 electrons. It has 17 electrons, but the rest of them are on the inner shells. Okay, so if you were going to draw what chlorine looked like, it's number 17, so it would have 17 electrons in this nucleus. And then the first shell, remember, always holds 2. The second shell could hold 8. Okay, so far that's 2 plus 8, that's 10. And then we have a third shell. The third shell can also hold 8. And the thing is, though, we've got 2 plus 8, that's 10, so we can only put 7 in the third shell. Sorry about the drawing. Okay, so we've only got 7, which means that we're missing one. So chlorine wants to have 8, and its outer shell only has 7. Once it has 8, all these shells are nicely filled up. It's got good balance. It doesn't, and the atom won't go out seeking more electrons. Okay, so chlorine, another thing is that the row corresponds to the number of shells. So chlorine has 3 shells. Okay, if we're looking at carbon, carbon is in the second row, so it has 2 shells. And it's number 6, so it has 6 electrons. Okay, but when we go back and think about what it looks like, because it has 6 protons and 6 electrons, and usually 6 neutrons in the nucleus, then again, that first shell is always going to have 2. The second shell usually would have 8. But remember, carbon only has 6, so we already used up 2. So that means that carbon only has 4 electrons in its outer shell. Okay, and that's what this drawing is showing. 4 electrons. Just like this one is showing 7. Needs 1 more here for the chlorine. For the carbon, it needs 4 to fill its shell. But it's not going to be able to get 4. Okay, so the electron dot structure is just showing the outer shell electrons. So you don't have to show all the inner shells, just the outer shells. Right? So for chlorine, you would just have 7. For carbon, you would just have 4. Okay, so anyway, usually I've got a big board to work on and a periodic table to show you on the wall. So I need to maybe put a few more materials in. Okay. All right, so again, the number of rows is the number of shells. And as you go over in the columns, the number at the top corresponds to the number of electrons. Okay, so now we want to look at an ionic bonding with sodium and chlorine. So sodium, go back to the periodic table. Here's sodium. Sodium is in column number 1. It's got 1 electron in its outer shell. That electron is sticking out like a sore thumb. It's easily ripped off because every time you add another shell, the atom gets much larger. So you add another shell. And if there's just 1 electron in its outermost shell, right, it's in the third one down. So it's just got 1 electron that easily can be ripped apart. So it's very vulnerable to having that electron ripped right off. Okay, so what happens is it loses that electron. And it will lose it to the chlorine. Chlorine, remember, has 7 electrons in its outer shell. It needs 1 more. So it will be happy to take the electron from the sodium. The problem is, once that happens, then you've got a sodium ion. There are 11 protons, 10 electrons, and so it has a positive charge. And you have a chlorine ion, which has 17 protons but 18 electrons. So it gets a -1 charge. And so what happens is now you've got something that's negative and something that's positive, and they're going to be attracted to each other. Okay, so what happens is in your lump of sodium chloride, you've got each sodium ion, the red circle, is surrounded by 6 chlorine ions. But also, if you look at one chlorine, it's surrounded by 6 sodiums. So they're surrounding each other. And so they make a big clump of material, and that makes table salt, sodium chloride. Now, for geologists, this is also a mineral. So it's also called halite or halite. So, so yes, so that's the name for sodium chloride, halite. And notice that it's very, very square, which reflects the beautiful squareness of the inner structure. Okay, so the covalent bond is where atoms have to share the electrons because they're not strong enough to pull the electrons off themselves and keep an electron. So they have a mutual attraction for shared electrons. And these form stronger bonds. Sodium chloride, you can dissolve that with water. But materials that have covalent bonds usually are not going to just dissolve in water. Okay, so sometimes this happens between 2 atoms that are equal in strength. And so like fluorine wants to join with another atom because it wants 1 more electron. It has only 7 in its outer shell. But if there's only fluorine around, then it will form a fluorine molecule. And the atoms share their unpaired electrons. And so then the fluorine looks out, um, and each fluorine can count on having 8 electrons now because the electrons that are in the center here spend their time zipping around both atoms. And so it brings balance to the structure. So that sharing works, the covalent bond works. And the atoms are very close together because the electrons have to zip around them both. Okay, now covalent bonds often occur between hydrogen. Hydrogen has only 1 electron, so it doesn't usually want to give it up all the way, so it often shares it with other atoms. So here we've got an oxygen. Oxygen, if you look at your periodic table, is number 8. So it's got 2 electrons in its inner shell, and then it has 6 electrons in the outer shell. So it needs 2 more, right? It's got empty spaces. And so the thing is that it will be willing to take the hydrogen's electron. It tries to rip it off, but the hydrogen doesn't give it up totally. What happens is that it turns into a covalent situation. They share it. These electrons zip around the hydrogen and around the oxygen. Okay, so they're sharing those electrons, and so the hydrogen isn't completely abandoned by its only electron. But again, covalent bonds then are very tight because the electron has to be shared. Okay, here's another common covalent material. This is ammonium, and so household ammonia. This is nitrogen with 3 hydrogens. Now that's because nitrogen is number 7. It's got 2 electrons in the inner shell and 5 electrons in the outer shell. Thing is, it needs 8, so it needs 1 electron from each of these hydrogens. But again, it will usually end up sharing. Okay, so what we end up with is all of these elements, um, all these atoms are now thinking that they have a filled shell, and the electrons do double duty around the 2 atoms. Okay, now another type of bonding is metallic bonds. So one of the reasons you can have a metallic bond with metals is that metals allow their electrons to move from one atom to the other very easily. So the electrons are only held weakly by the nucleus. So the electrons move around freely, and so they jump from one atom to the other. So the atoms are sometimes a little positive, sometimes a little negative, depending on how many electrons they have. And so what happens is that they hold together because of this constant um, change in their charge. And so they are holding together, but it doesn't have to be in any particular structure. So you can have copper mixed with silver, mixed with gold. These are called alloys, and the metallic bonds make that possible. There's no definite proportion. Anyway, mobility of electrons accounts for many metallic properties, such as the idea that metals conduct electricity, because the electrons can flow from one atom to the next atom to the next atom. They're also good conductors of heat for that same reason. Electrons can flow and carry heat energy with them. So electricity and heat flow. Okay, now here's the alloy idea again. An alloy is a mixture of metals. Um, you don't have to have any specific proportion. There's yellow brass, and the recipe for yellow brass is here. 67% copper, 29% zinc, 3% lead, 1% tin. But there's also red brass. And then there's bronze, which is slightly different. And so you have these different alloys because they don't have a definite proportion. So they wouldn't be considered minerals in that case. Okay, the last thing we really want to talk about are isotopes. And then we want to talk about different varieties. Okay, so what's an isotope? Isotopes are when you have a certain number of protons, but you have different numbers of neutrons. Okay, so we're looking at the mass of the nucleus, the protons and the neutrons. So the mass number is the sum of the neutrons and protons in an atom. So let's take carbon-12. Carbon-12 is an isotope of carbon. Now carbon will always have, so carbon-12. The 12 is referring to the number of protons plus neutrons. Carbon is always going to have 6 protons. But the number of neutrons can vary. It's always got 6 protons to match its 6 and 6 electrons. But neutrons can vary. But carbon-12, it's 6, 6. And then for the electrons, it's 6 also. Okay, but there's also carbon-14. This is another isotope. What's the difference? The number of nucleons. The number of nucleons is the number of protons and neutrons. But since it's still carbon, then it's still going to have 6 protons. But to make up the number 14, it's now going to need 8 neutrons. But to keep it neutral, it's still going to have 6 protons. Okay, so the isotope has the same number of protons for that element, but different numbers of neutrons. What happens is, we're going to talk about radioactivity in later chapters, but some isotopes are unstable and they emit particles and energy. And so we'll be talking about that more in different chapters. Chapter 10. Okay, this is just a quote by Nikola Tesla. I'm not sure what it means exactly, but it's kind of cool. All right, we cannot understand the life of a crystal, and yet it is a living being. Okay, perhaps. Okay, so crystals grow. Remember we started talking about how crystals that have nice faces usually grow in open chambers. So crystals grow by solidification from a melt or precipitation from a solution. And so what you have is you've got a solution here, and it has particles that gradually add on, and they help crystals to grow. So the crystals get bigger and bigger. They expand outwards. Now, you have nice faces where there's room, but when they start to jam together, then you just get a jumbled mess. Compact solid. Okay, so if you want pretty faces, then you have to catch them at the right stage while they're still beautiful, because eventually they will smoosh together. Okay, now another thing that's in this section is about polymorphs, and this is the last thing we're looking at for this part. Polymorphs are also called allotropes. Poly means many, and morph is talking about shape, okay, or appearance. Polymorphs, many appearances. So polymorphs have different kinds of bonds. And diamond and graphite are both carbon polymorphs or allotropes. They're made of carbon, they're pure carbon, but diamond is the strongest, hardest mineral, whereas graphite is very, very weak. And so diamonds get their strength from their complex structure. As you can see, they're all tight and wound around each other, making these beautiful tetrahedral type connections. Very, very strong. Whereas graphite makes these hexagons, and those are strong, but then they only weakly connect to layers of more hexagons below them. And so because of that, you can slide pieces off. So graphite, of course, is what's inside pencil lead. So when you write, you're scraping off layers of these hexagons. And those are getting left behind on your paper. So that's leaving your mark. Okay, now, a few years ago, people started to look into what else could carbon do. They started to look in soot, and they found that carbon could take on several other very interesting forms. So we talked about diamonds and graphite, but this strange thing is called the buckyball. Its full name is Buckminster fullerene. And that's because the people who saw it, who first discovered it in soot, they looked at it and they said, well, that looks like a geodesic dome design. And the architect who designed the geodesic dome, his name was Buckminster Fuller. First name Buckminster, last name Fuller. So they named it after him, and we call it buckyball for short because otherwise that's a really long word. Okay, and it has 60 carbons in a sort of soccer ball pattern. And when they looked in soot at the same time, they found what are called nanotubes. So the ring-like structure that's in graphite is now forming a circle, a cylinder. And then later they figured out too, what would happen if you just took one layer of the graphite? Well, if you just had one layer of it, that becomes a whole new material called graphene. Now, all of these materials have different properties. They're all pure carbon, but they're all different. And again, polymorphs, another word for them is allotropes. Okay, so graphene is incredible. It's strong. Someday it may be semiconductors, it may be smart paper, because it will conduct electricity, which is very cool. It also has, it conducts heat too. So it's very, very useful, better than silicon potentially. And there are lots and lots of things that people are thinking they might use graphene for. If we had time, we would talk about them. Okay, so, but you can look it up online. Lots of cool stuff. Okay, nanotubes. They found they can close off an end of a nanotube, stuff cells inside them, atoms inside them, and they can become detectors or be put in paints. They can even put them together and make tiny little machine parts or squish them down to make batteries. Anyway, so there are lots of ideas for nanotubes also. Okay, so that's the end of part 1, and we will do part 2 next time. Okay, thank you. See you later.